Hello, welcome back. So today we are going to discuss about the diode models and as we use them in our circuits. So let's begin. So small semiconductor, big effect. The diode is both simple and full subtle. So today we'll learn the practical models you actually use in a circuit and why each model exists and how to find the diode operating point using the load line. By the end, you will be able to know to use the ideal diode when a constant voltage approximation is okay and how to apply the Shockley's equation properly. So our objective today is, so let us list them out here. So we will be understanding three diode models, then we'll do load line analysis graphically, and then number three, use the Shockley's diode equation for accurate currents and then solve few circuit numericals. So why these models are required? So real diodes have an exponential IV characteristics as we can see here in this graph. So which we normally use whenever we are using or discussing the diodes. Now, but for solving circuits with exponentials every time will be painful. It will be quite difficult to use. So that is why engineers have made more simpler models depending on the problems. And quick estimate to use the constant voltage model, like circuit design uses piecewise linear model and precise analysis uses the Shockley's equation. So now as we are discussing about the diode models, so diode models is of three types. So first model is known as the ideal diode. So ideal diode model. So what is ideal diode model? So if we consider a circuit diagram, a simple circuit diagram containing a diode, and the circuit is connected in the forward bias operation. So let us also consider a resistance R. This is the diode D, and this is suppose the voltage VDD, and the current moving is suppose ID. Since this is forward bias, so what will happen is the current will flow. So if we write down the KVL equation here, so it will be VDD equals to ID into R plus VD, the voltage drop across the diode. So this is the KVL equation of the diode circuit. Now let us consider if we are talking about an ideal diode. So how it will be or what will be the corresponding response. So first let us see the response. So if we plot the response of the ideal diode in the forward bias, it should conduct current immediately, and in the reverse bias it should not conduct any amount of current. So this would be the graph for ideal diode, in which what we found is this is the input voltage or the forward bias voltage, and this is the forward bias current. So ideally diode should conduct in the forward bias and diode should not conduct in the reverse bias. That should be the ideal case. That means whenever we are drawing this symbol, then this represents only the diode. So ideally allowing current in the forward bias and doesn't allow current in the reverse bias. Okay, so this should be the ideal diode. Now let us moving forward. If we have constant voltage drop model, so what is the change that we can see in this model? So let us again draw the axis. Now in constant voltage drop model, what should be the case? That after zero point 0.7 volt, the diode should be conducting because of the depletion layer, as we already know this. So the current should conduct immediately after zero point 0.7 voltage. The reverse bias, there should not be any current. So this is called as constant voltage drop model, where we have a threshold voltage of 0.7 volt in case of silicon and 0.3 volt in case of germanium. Okay, so this is constant voltage drop model. So as we can see here in this model, what we are having is, if we draw the diode, then it will be something like this, that we should have an ideal diode, and then we should have a supply of this value. Suppose this value is Vt, so this should be Vt, and there should be a constant ideal diode. So this is constant voltage drop model. Now moving forward, next on the agenda is piecewise linear model. So piecewise linear model. So it is slightly upgradation of the constant voltage drop model. So as we have considered in constant voltage model, so the conduction should take place after 0.7 or the Vt. Now in piecewise linear model, after this, the graph will have a linear response, or it will increase linearly. So that represents a constant voltage drop model, and due to this, we'll be having a resistance. If we measure the resistance here, then it will be coming as Rd. Okay, so now if we draw the diode or represent the diode with respect to all the conditions, so it should be a ideal diode first, then it should contain a supply for this voltage drop Vt, and for the linearity, it should contain a resistance, that is Rd. Okay, so these are the three models of a diode. So we had discussed ideal diode, constant voltage drop model, and the piecewise linear model. So let us consider a numerical for diode models. So now here what we have is the voltage V on, or the diode voltage is 0.7 volt, and the resistance is given as suppose 10 ohm, and the input voltage Vs is suppose 5 volt. So along with that, we have the resistance is given as 1 kilo. That is a simple circuit containing a diode supply, which is Vs. Then we have a diode, ideal diode. Then we have a voltage drop, constant voltage drop model. So it is 0.7. Then we have piecewise linear configuration, for which we are having a resistance of 10 ohm, and the resistance of the load is given as 1 kilo. Okay, so what we have here, so in a numerical we have Vn equals to 0.7, Rd equals to 10. So Rd means this is Rd, 10 ohm, and then output load is given by 1 kilo ohm, and then the diode knee voltage, or the threshold voltage, is given as 0.7 volt. So now after writing the KVL in this loop, what we're going to get is Vs equals to 0.7 plus current multiplied by Rd, which is 10, plus current multiplied by 1 into 10 to the power 3, right? So now from here, if we determine the value of I, so it will be, now this Vs is nothing but 5 volts. So from this we will be subtracting the value of 0.7, then divided by, it is 10 plus 10 to the power 3 means 1000. So this will come out to be 4.26 milliampere. So it is as simple as that. So now moving forward for diode current equation. So diode current equation is required for the precise calculations considering the exponential behavior. So this gives the diode current as a function of voltage and exactly under ideal assumptions. So the equation is given as I equals to I naught e to the power v by eta vt minus 1. I is obviously the diode current. Then I naught is the diode reverse saturation current at room temperature. Then we have voltage V, which is the external voltage applied to the diode. And next, eta is a constant. So here, the value of eta for germanium is given as 1, and then eta for silicon is given as 2. Okay, so as per our requirement, we'll choose the value of eta. Then the value of Vt, as we already know, is nothing but kT by Q, which is T by 11600, which is nothing but the volt equivalent of temperature, as we have discussed in the earlier class. Volt equivalent of temperature, that is Vt. Then here obviously K is Boltzmann constant, and the Q is, as we already know, is charge of the electron. And finally we have T, which is the temperature of the diode. Okay. So this is representing the diode current equation. Okay, so let us consider this numerical. So the numerical states that the reverse saturation current of a PN junction diode is 10 microampere, and we have to calculate the diode current for forward bias voltage at 0.6 volt working at 25 degrees centigrade. So now here the value of Vp is given as 0.6 volt, the input voltage. The temperature is 28 degrees centigrade, so 273 plus 25, so which is 298 degree Kelvin. Now we have I naught value as 10 microampere, and the forward bias voltage is 0.6, so this is silicon, so value of eta will be 2, and Vt will be equals to T by 11600. So putting the value, we'll be finding it as 25.7 millivolt. So now the value of diode current equals to I naught e to the power V divided by eta Vt minus 1. So now putting the values, we'll get the current as 1.174 ampere. So this is a straightforward question where we have to determine the diode current. Now moving on to another numerical. So the second numerical states that the diode current is 0.6 milliampere when the applied voltage is 400 millivolt, and 20 milliampere when the applied voltage is 500 millivolt, and we have to determine the value of eta. So, and also given assume room temperature. So at room temperature, value of Vt is 26 millivolts, that we already know. So now here what we have is I is given as I naught e to the power V by eta Vt, so that Vt we can write down as kT by Q, minus 1. Now we have value of V is very much greater than Vt. So then what we can consider is, so for the first part, that is 0.6 milliampere, we have this is I naught, then e to the power, this whole term will be 400 divided by eta, then the remaining part, which is 26 millivolts, 10 to the power minus 3. Then this minus 1 can be neglected considering the input voltage is higher than unity. Then this will be given as I naught into e to the power 16 by eta. So this is 16 into 10 to the power minus 3. Next, similarly for the second part, that is 20 millivolts. So the equation will be given as I naught after simplifying. So we have this as 20 by eta. Now if we take ratio of these two, so let us consider the bigger term on the top. So I naught will get cancelled. So this is e to the power 16 by eta. And next is e to the power 20 by eta. So now if we simplify this, then this is 100 by 3 equals to e to the power 4 by eta. So if we take log, then 4 by eta equals to ln of 100 by 3. So from here the value of eta will be coming as 1.14. Okay, so this means this is a case for germanium semiconductor, because as we know, in case of germanium value of eta is 1. So like this we can solve numericals for diode current equation. Okay, so now let us move into the next topic, which is diode resistance. So as we know, in forward bias and reverse bias, diode operates differently. In forward bias, we have current in milliampere range, and in case of reverse bias, we have current in microampere range. So considering this factor, what we can understand is the resistance of a diode is different for both forward and reverse bias conditions. So first, let us consider the characteristics first. Then we'll see how to derive the value of a diode resistance. So if this is our axis, so we have here forward voltage, forward current. This is in milliampere range. This is volt. Then here we have reverse bias voltage, and this is reverse bias current, which is in microampere. So if we draw the characteristics, it will be something like this. In the forward bias, and in the reverse bias, it will be something like this. Right? Now, in order to determine the resistances, so diode resistance are of have different names. So first one is the forward resistance. In forward resistance, we have two names. That means two types of resistances are there. First one is called as DC or static resistance. So in case of DC and static resistance, it is defined as the ratio of voltage to the current, where V by I is the forward bias characteristics of the PN diode. So as the static resistance varies widely with V and I, hence it is not very much of useful. That means here in static resistance we will consider any point on the diode curve or the diode characteristics. Suppose we are considering this point. So across this point, we will have a value of voltage. Suppose we are having a voltage Vx and we are having a current Ix. So for the voltage Vx, we are having a current Ix. Then the static resistance will be given as Rf equals to Vx divided by Ix. Okay. So this may vary throughout its characteristics, because if you consider the static resistance point here, we'll have a different value. Similarly, if you are considering it here, we'll have another value. Similarly, in any other point. So this will vary. So that is why it is not of that significance. Instead of that, what we do, we calculate for AC or dynamic resistance. So in AC or dynamic resistance, we consider a range. That means the AC resistance is given by, or dynamic resistance is given by, Rf equals to delta V by delta I. So that means, suppose two voltage and two currents, V2 minus V1 and I2 minus I1. Now let us consider another point. So if we consider, suppose this point. So for this, we will be having corresponding values of voltage and current. So suppose this voltage is V2, this current is I2. Now we are taking another point, suppose somewhere here. So we have V1 and we have I1. So the dynamic resistance is given by this relations, where we subtract V2 from V1 and I2 from I1, and the ratio will give us the resistance. Now this value will almost be similar in any region of the diode characteristics, since we are considering it by a difference between two values, and those two values we consider very far apart from each other. So this is called as the AC or dynamic resistance. Now this dynamic resistance has some relation with the diode current. So this is given as Rf. As we know, resistance is inversely proportional to current. So this is given by eta Vt divided by the diode current, where we know Vt is volt equivalent of temperature given as T by 11600. And in room temperature, this we consider as at 26 millivolts. Okay, so this is our AC or dynamic resistance and its relation with diode current. Now, the third point is the reverse resistance. Reverse resistance means the resistance that we observe across the PN junction diode during its reverse bias condition. So it is very much larger compared to the forward resistance. It is very much higher. If the forward resistance is in ohm range, then the reverse bias or the reverse resistance will be in a range of mega ohm. Okay, so if we quickly see a numerical on this topic, so suppose we have to determine the forward resistance of a diode when the forward current is suppose 5 ampere and T is given as suppose 300 degree Kelvin. So this is the question. Determine, these are the parameters given. Forward current is 5 milliampere and T is 300 degree Kelvin, and we have to determine the dynamic resistance. So in order to determine dynamic resistance, we will be using this formula. So Rf equals to eta Vt divided by I. Now since it is a silicon diode, so for eta we will be putting it as 2 multiplied by Vt. We already know the value of Vt is coming from T divided by 11600. So put here the value of T as 300 degree Kelvin and divided by the current, which is 5 milliampere. So after putting the values and equating, we'll be getting the value of the resistance as 10.34 ohm. Okay, so I hope you have understood how to calculate the diode resistance. So if you have any doubt on diode resistance, then you can put it in the comments. So next point is load line of a diode. So let us consider a forward bias condition of the diode. That means this circuit, as you can see here, this is the VDD input voltage, and there is a resistance R, and this is the diode, and the voltage drop across the diode is VD, which for silicon is 0.7 volts, and the current is ID. So for this, if we draw the characteristics, so this will be the characteristics of the diode, right? So now in this, if you write down the KVL equation, it will be VDD minus IDRD minus VD equals to 0, right? So now what is a load line? So load line is a graphical representation used in the analysis of the diode circuits. So each illustrates the relation between current and the voltage across the diode, helping to determine the operating point of the diode. So that means the relationship between current and voltage will determine the load line, which will represent the characteristics or the operating region of the diode. And by determining the Q point, we'll be able to determine the operating point of the diode circuit. So before going into key point, let's see what is load line or how to determine load line. So to get the relation between current and voltage, so first let us consider the voltage is 0, diode voltage is 0. So if we consider this, then the equation will become as VDD equals to IDRD, right? Considering the voltage equals to 0. That means we have to determine the relation of the input current and the input voltage at 0 voltage and 0 current. That means whenever we are having voltage as 0, then this is the 0 voltage. Now at that time, what is the value of the current? So the value of the current is given as ID equals to VDD by RD. So that point may be somewhere around here. So this is VDD by RD, right? Now next will be ID equals to 0. That means at 0 current, what will be the voltage? So if you put this here, the D will be equals to VDD. Okay. So this voltage, whatever voltage applied voltage we use, that will be the voltage. So this will be lying somewhere around here. So depending on the value, you can determine the exact point. Right. Now, after joining these 2 points, the line that we are getting is called as the load line. And wherever it meets with the characteristics is known as the Q point or quotient point or operating point of the diode. So that means the diode is working at this point, which means the value of voltage and current are given by these two respective values. So suppose VDX and this is suppose IDX. So this is the value where the diode is working. So this is the load line of the diode. So this is the characteristics, diode characteristics, and this represents the load line. Okay, I hope you have understood this. So let us also consider a numerical for this one. So we have the value of VDD is 10 volts. Considering the same circuit, VDD is 10 volts. Then the resistance, this is RD. The value of resistance RD is 1 kilo ohm. And the diode is considered a silicon diode. So value of VD is 0.7 volts. Okay, so we have to determine the load line and then determine the Q point. So to determine the load line, ID max is given as VDD by RD at VD equals to 0, which will be 10 volt divided by resistance 1 kilo ohm. This will be 10 milliampere. So if we plot, then this is at somewhere around, suppose let us consider a scale which will be giving us 10 milliampere here. So the value of the voltage is given as VDD considering ID equals to 0. So this is nothing but 10 volts. So suppose let us consider using a proper scale, this value is somewhere around here. Okay, now if we draw, this is our load line. Now to determine the Q point, as we know, the Q point should intersect with the diode characteristic. So since this is 10 volts, then this will be somewhere around this 5 volt. So accordingly 1, 2, 3, 4, 5. This is 1 volt. So now what we know that the diode characteristics will never go beyond 1 volt. So it will be somewhat like this up to this point, and then it will be somewhere around like this. So the Q point will be given by this value. So using proper scale, if we see, this value will be coming as 0.8 volt and the current will be around 9.25 milliampere. So using proper scale, this will be the value. So now moving further, we have the last discussion of today's class, that is small signal analysis or small signal model of a diode. So for this, let us consider an example, and then with that example we'll discuss how to solve it. So first let us consider a circuit diagram. So this is the example where we have to determine the value of current ID. Now first, whenever we have to go through this type of numerical, first we have to check whether the diode will be operating or not. Because if the diode is not operating, then there is not any requirement even to solve the circuit. So here if we see, the value of V2 is given as 15 volts, so 15 volts will appear here, and similarly V1 is 10 volts, so this is 10 volt. So considering this 15 volt and 10 volt, the diode is in forward bias condition, as this is at higher potential than this point, so the diode is at forward bias condition. So now we can solve the numerical. So now considering nodal analysis, if you write down the equations, so this is suppose point A, this is suppose point B. So the equation will be at this, as we already know that we consider the current to be moving outward. So if you consider that, so it will be VA minus V1 divided by 10K plus the current is in the opposite direction, so we have to put it as a minus. Then we have VA divided by 10K. So instead of K, you put into 10 to the power 3. Then for the second node, this is at node A, and for the second node, that means at node B, it will be ID current moving outward plus VB divided by 10K or 10 to the power 3, then plus VB minus V2 divided by 10K equals to 0. This is also equals to 0. So now adding these two equations, which will eliminate ID, so we'll be having the value of, after simplifying, so 2VA, it will be 2VA plus 2VB minus of V1 minus of V2 equals to 0. We already know V1, V2 values, 10 volt and 15 volts. So if we put them here, then this is 2VA. Now VA can also be written as VB minus 0.7. This voltage drop is 0.7. So VA can also be written as VB minus 0.7, then 2VB equals to V1 plus V2. So V1 plus V2 is 15 plus 10 is 25. So from here value of VB can be determined, so which is nothing but coming out to be 6.6 volts. Now VA is VB minus 0.7, so which is equals to 5.9 volt. Now determining the value of ID, considering any one of these two equations, by putting the value of VA and VB, we would calculate the value of ID, and that will be coming as, after calculation, 0.18 milliampere. So this is the answer, the required value of ID. So like this we can solve any numerical for small signal model of a diode, and here the diode that we have used in this question is a constant voltage drop model. So I hope you have understood all the points that we have discussed today. So in our discussion we have started our discussion with, first we have considered the diode models. So we have considered all the three diode models. Those are ideal diode, constant voltage drop model, and piecewise linear model. Then we have seen what is a DC load line, and the DC load line, the analysis, and the numericals also we have gone through. Then we have determined the or discussed the diode equation and how the diode equation can be used for solving numericals. That also we have seen. Then we have also seen, along with that, the diode resistance, how we determine the diode resistances and corresponding numericals. And finally, we have seen the numerical on small signal analysis of a diode. So I hope you have understood all the points that we have discussed today. So if there is any doubt, you can put it in the comments so that we can go through those comments and give you the answers as soon as possible. And if required, if your query is big enough to discuss in a class, so we will be discussing that in our next class. So till then, keep learning and keep joining our classes. So if you feel it interesting and helpful, then please do like, share, and put your comments, and also please subscribe so that you don't miss any video whenever we are updating. Thank you.